Okay, so today we're going to be talking about the electromagnetic spectrum and calculating the energy of a photon. So real quick, I'm going to go back over from the last video just the basic formulas for calculating wavelength, frequency, just things that we need to know before we can move forward. All right, so if you remember, we had c, which is the speed of light, is equal to lambda times v. Lambda being the wavelength in meters, and v equaling the frequency in hertz. So I'm going to write down over here some stuff that we need to know. So c equals 3.0 times 10 to the 8 meters per second. Lambda equals your wavelength in meters. And v equals your frequency in hertz. So this one's going to be m, and this will be seconds to the negative 1 power. All right. So if you just had a basic wavelength problem, you would just have to rearrange this equation. So to calculate wavelength, you have c over v, and to calculate frequency, you have v equals c over lambda. So I'll label those real quick. So this will get you wavelength, and this will get you frequency. You just have to make sure that everything's in the appropriate units, or you're going to get the wrong answer. Alright, so if you need a second to copy any of that, feel free to pause the video, but I'm going to keep moving. So, alright, real quickly, we're going to add something new to this so we can actually calculate the energy of a photon. So right now we can only calculate if it's wavelength and calculate its frequency. So we're going to need something called Planck's constant. So Planck's constant essentially is the proportionality relating a photon's energy to its frequency. So this relates photon energy to its frequency. This is super, super important. All right. So, anyways, Planck's constant is represented by a lowercase h, and it is the most common way that I've seen it written. This is how I always do it. 6.626 times 10 to the negative 34 joules seconds. All right. So now, if you want to calculate the energy of a photon, we're going to need this equation. E equals h times v. So this right here gets you the energy of a single photon at that particular wavelength or frequency of electromagnetic radiation. So it looks pretty easy because it is. All right. So if you don't know, joules is a measurement of energy. But anyways, I'm going to show you how to use this. So oftentimes you are not going to be given V if your teacher, or if the equation that you have is going to be requiring you to solve for the energy, because most of the time when waves are measured, we measure the wavelength. You can obviously convert it, but instead of doing that, you can just plug this into there, and it'll give you the same answer. H times C over wavelength. And this will give you the same thing. You just have to make sure that you have the appropriate units. So I'm going to do an example real quick. Very easy one. So, we observe a photon of EMR, electromagnetic radiation, with a wavelength of, I don't know, I'm just going to make a number up, 125 millimeters. What is E? So what is the energy of one photon at that wavelength? All right, so first thing we have to do is we have to convert this into meters. So 1 meter equals 1,000 millimeters. So let's convert this. 125 millimeters times 1 meter over 1,000 millimeters. This is gone, equals 0.125 meters. Now we can use our formula to calculate the energy of a photon. So we have E equals h times c over lambda. So we're going to have E equals 6.626 times 10 to the negative 34 joules seconds times 3.0 times 10 to the 8 meters divided by seconds divided by 0.125 meters. So if we look, that's going to cancel and our seconds is going to cancel. So we're just going to be left with energy, which is what we want. So let me open up my calculator and we'll plug this in. So we have 6.626 EE negative 34 times 3 EE8 divided by 0.125. And we're going to get about 1.59 times 10 to the negative 24 joules. So E equals 1.59 10 to the negative 24 joules. And that would be the answer. So as you can see, it's really not that hard of an equation to use. But anyways, give me 1 second because I'm going to copy and paste something into here. Alright, I'm going to go to the next page. So this might be a little difficult to read, but it'll be alright. Alright, so I took this problem from, I forget what website, but they're really good. I think it's Chem Team. So anyways, the human eye's optic nerve needs 2 times 10 to the negative 17 joules of energy to trigger a series of impulses to signal the brain there is something to see. How many photons of 475 nanometers blue light are needed to trigger this response? Alright, so we're given a lot of information there. We know that right here we have, I'm not going to keep that highlighted, but we have 2 times 10 to the negative 17 joules is needed for that series of impulses to trigger in our brain. So we're going to have to keep this number in the back of our head. We also know that this is the wavelength of light we're using. So we need to convert this to meters. So let's set up the problem. So we have E equals h times c, because we're already given 2 things. We just have the wavelength and it just needs to be in meters. So let me put the conversion factor. 1 meter equals 10 to the 9 nanometers. And then just like GWiz info, anytime you have something in nanometers, you're going to end up with a number between 1 and 10 times 10 to the negative 7 meters. So to do this, we're going to have 475 nanometers times 1 meter divided by 10 to the 9 nanometers. Alright, so anyways, we're going to end up with 4.75 times 10 to the negative 7 meters. So this is equal to lambda. So now all we have to do is we have to first figure out how much energy is needed for one photon, or how much energy is one photon going to be producing. So E equals Planck's constant times the speed of light divided by the wavelength of our photon. Alright, so that's gone That's gone. So let's plug this into our calculator. Oops, definitely not that. I'm going to just redo it just in case. And then divided by 4.75 EE negative 7. Alright, so the energy of one photon is going to be equivalent to 4.18 times 10 to the negative 19 joules. Alright, so that is equal to one photon. So the question was, how many photons of this wavelength are needed to trigger a response? So 2 times 10 to the negative 17 joules equals x photons. So we just have to set up a little inequality, or not inequality, a little equation to figure this out. So I do x photons over 2 times 10 to the negative 17 joules is equal to 1 photon divided by 4.18 times 10 to the negative 19 joules. So to solve this, essentially, instead of cross multiplying, just look at this. All you have to do is 2 times 10 to the negative 17 joules on both sides. So x photons is equal to 2.0 times 10 to the negative 17 joules divided by 4.18 10 to the negative 19 joules, and then that's times 1 photon. So the joules are going to cancel out, and you're going to be left in units of photons, which is what you want. So let's plug this into the calculator. So this is going to give us our answer. So we have 2 EE negative 17 divided by, and I'm going to just plug this in, be the same thing. So you're going to get about 47.79. All right, so anytime you have a decimal point, even if it's like 0.01 or 0.001, the fact that you're talking about particles or the amount of particles you have, you just round up. It doesn't need to be the 0.5 rule. It's because you don't have partial photons. So the answer to this is going to be 48 photons. And that is how you use Planck's constant to equate the frequency to a photon's energy. And that's how you calculate different types of equations with this. So if you have any other questions, you can ask me in class.